Okay, so this is the first of 3 recordings that I want you to work your way through in this first week of class, and all 3 of these are going to be over what I would consider review material. In fact, I just have this on the PowerPoint, the review. Right? The first one is over thermodynamics, and it's going to be covering essentially topics from Chapter 13, pages 506 through 511. The second one is going to be, I'm going to call it Reactions of Biological Importance. It's a review of organic chemistry. It's going to be on pages 511 through 517, chapter 13 again. And then the last one is going to be over material from pages 517 through 523 in your book, essentially the molecule ATP. I want you to listen to these. I want you to read those. I'm going to hold you accountable for the material in this recording as well as the book, on quizzes as well as exams. So make sure that you understand this material. It is review though. So you've gone through Gen Chem 1, Organic Chemistry 1 and 2, Gen Chem 1 and 2, as well as many biology classes. For some of you, several biology classes, and certainly you've talked about these things before. So I don't want to spend time in class, but I also want to make sure that we all are on the same page with this material. All right, so let's move forward and let's think about thermodynamics here. And we're going to start our discussion with the laws of thermodynamics, just the first 2 laws of thermodynamics. And we're going to boil that down into a discussion on free energy changes, again, topics that you're familiar with, and we're going to be thinking about essentially how these are going to be thought of in our course. So let's look at the first law of thermodynamics. And the first law of thermodynamics, as I'm sure all of you know, states that energy cannot be created, nor can it be destroyed, only conserved from one form to another. So conservation of energy, conservation of matter, very important topic. Energy is transformed from one form to another. It's essentially transferred from system to surroundings or from surroundings to system. Now, you can think about this in terms of astronomical scales. The first law of thermodynamics essentially states that the total amount of energy in the universe is not changing. It's a constant value. However, the form of that energy is constantly changing, and there is always going to be these energy transfers from system to surroundings and surroundings to system. That's on an astronomical scale. Of course, we're going to think about much smaller universes, if you will. A universe is simply a system plus its surroundings. So, for instance, we could define our system as a beaker with reagents in it and the surroundings a reaction vessel. We could think about a system as being a cell or an entire biological organism. So they can be very simple systems or they can be very complex systems. And it all would be dependent on how we define the system. Now the surroundings is then everything else, and then the system and surroundings is the universe. Now let me try and illustrate something here about the first law of thermodynamics using the universe being your kitchen, a small universe. And some of you might think to yourself, I like this universe. My kitchen has yummy things in it. That's good. Okay, so a yummy universe, let's say. And we're going to define our system in that universe as a stove on your burner, and then everything else as part of the surroundings. And we'll start with the stove as red hot, and then we will turn the stove off. Now, what's going to happen? Well, the stove, right, the burner on the stove is going to cool down, and according to the first law of thermodynamics, the temperature in the room is going to increase. What's happening is energy is leaving our system, the burner, and going into the surroundings, the rest of the kitchen, and the temperature of the rest of the kitchen is going to increase while the burner goes down. That's consistent with what we call the first law of thermodynamics. The total energy in our universe hasn't changed. It's just been transferred from system to surroundings. Now, think about this in biology. There's going to be lots of different ways that we're going to think about this. But there's going to be, for instance, energy that would be inherent in the molecule glucose. Well, in the first several weeks of class, we're going to be thinking about how glycolysis, the citric acid cycle, as well as oxidative phosphorylation are going to take that energy in the form of the bonds between carbons and oxygen, and we're going to see how that energy can be then conserved or moved to ATP. in what would be considered a phosphate anhydride bond in the ATP molecule, and then that energy is going to be used to do something else. So that will be, again, the first law of thermodynamics. Energy is changing shapes, changing forms. It's being moved from one area to another, but it's not, the total energy is not changing. Okay? Now, the second law of thermodynamics is going to then take this idea one step further, and it's going to give us some idea of which direction energy is going to flow spontaneously. And so this is several ways to state the second law of thermodynamics, but the entropy of the universe is always increasing. That's probably the most common means of stating the second law of thermodynamics. Entropy is this idea of disorder. We're going to be thinking about it in terms of energy. Energy can take on a more ordered form or a less ordered form. And the entropy of the universe is always increasing. There's always going from order to less order, more chaotic. Right? Now, I honestly think that this is going to be, and the direction that we want to take this conversation is more easily stated when we say this. Second law of thermodynamics states that the direction of spontaneous energy flow is always toward the state of maximal entropy. Spontaneous energy flow is always going toward the state of maximal entropy. Okay? Now, understand this. We talk about energy flow here. Okay, let me introduce this idea. Work is an orderly transfer of energy. So an orderly transfer of energy. That's work. And so when we think about this, essentially if you take a universe, it's always going towards a state of maximal entropy. What's happening is that the energy is essentially decreasing in its ability or capacity to do work. That's essentially what the second law of thermodynamics is stating. Now, let's go back to our illustration with our kitchen. We have a burner that's red hot. Well, we turn off the burner. And what if the burner, instead of going from red hot to cooler temperatures, what if it went from red hot to white hot? That could happen. According to the first law of thermodynamics, it could happen so long as the temperature of the surroundings decreased and the temperature of the burner increased. That's perfectly consistent with the first law of thermodynamics. However, that is not consistent with the second law of thermodynamics, because the second law of thermodynamics states that energy will disperse. It will go down a thermal gradient from hot to cooler, not from cooler to hot. And if you think about energy transformations happening in gradients, and you actually are going to be well served in this class. Energy is going down gradients. It's moving like a concentration gradient. It will move down a concentration gradient. It will move across electrical gradients. There will be electrical potentials that we'll talk about. It'll move across chemical potentials that we'll talk about. And so there's all sorts of different gradients that energy is going to move with. And they're always going to go, according to the second law of thermodynamics, it's always going to spontaneously, meaning without any help. So it always go down that gradient, not up it. Okay, that's what the second law of thermodynamics states. So really, the second law of thermodynamics tells us which direction the energy is going to flow. The first law tells us that energy is going to flow. Right. So now understand something, going back to our burner analogy here. Understand that the spontaneous movement of energy from the burner to the surroundings, right, that's where it's going to go, from the burner to the surroundings, is going to happen until finally that system reaches equilibrium. And so let's then talk about equilibrium, very important concept. Equilibrium, there's lots of ways to think about this. Let's define it as this, where the free energy of the system has been minimized. And what exactly do we mean by free energy? Well, free energy is essentially G. Gibbs free energy is how I'm sure you've encountered in other classes. We're going to look at changes in Gibbs free energy in the upcoming slides. But free energy, or Gibbs free energy, is just essentially the work or energy in a system that can do work. In a system that does work. And work, remember, is the orderly transfer of energy. Now, let's try and illustrate what exactly we mean by that. Oops, I moved in the wrong way. What exactly do we mean by energy in a system that does work? Well, let's think about a bucket. And we're going to put that bucket on a bucket of water. We're going to put that bucket of water on the ledge of a 3-story building. And in that bucket of water, there are lots of different energy terms. For instance, there's the temperature of the water, which is just the average kinetic energy of all the molecules. There's the temperature of the metallic bucket. There is the energy found in the hydrogen bonds between the water molecules. There's the energy found in the covalent bonds between oxygen and hydrogen in the water molecules. There's all sorts of energy. There's obviously gravitational energy. There's a potential there for that to fall. It's being pulled towards a large object. There's gravitational energy there. So which of those can do work? Well, when you think about our bucket of water really sitting on the edge of a 3-story building, certainly the way I've depicted this, the gravitational energy is going to do the work. That would be our free energy then. That's the portion of the total energy of the bucket of water that's going to do work in our system. Okay, so that's what we think about when we think about free energy. So when we think about equilibrium then, equilibrium is where the free energy of the system has been minimized, meaning that that energy in the system that could do work is no longer there. So when we think about a system that's at equilibrium, then we think about a system that can no longer do work. Think about our burner. All right, once it reaches equilibrium with the room, then there's no longer an orderly transfer of thermal energy from the burner to the room, and therefore there can no longer be then work done. Before that, there was this orderly transfer of energy from the burner to the room. That's work. Okay, once equilibrium has been established, it's no longer there. And so when we think about the second law of thermodynamics, it's directly related to this idea of equilibrium, where we can think about this as being free energy has been minimized or entropy has been maximized for the system and the surrounding. And we say that that system, that surrounding that has reached equilibrium, that universe that's reached equilibrium, can no longer do work. There's no longer orderly transfers of energy. So that's your first and second law of thermodynamics and their relationship to equilibrium. Now, let's take this then and think about the implications and go back to astronomical scales. We think about this, and you'll oftentimes hear this, that the universe has some beginning in the finite past. The universe has some age appended to it by scientists. Okay? And when we think about then the beginning of the universe, what are the evidences that support that idea? Well, one of them is found in the laws of thermodynamics. If the universe has always existed, meaning that time is infinite for the universe, that means that then enough time would have elapsed for all energy transformations to have taken place, and the entire universe would be at equilibrium. But we're not at equilibrium yet, so that suggests that the universe isn't infinite, that it began sometime in the finite past. Now, at the same time, that also tells us that, the universe is dying. It's reaching equilibrium. The end of the universe is coming. So you heard it here in biochemistry. The end of the universe is coming. In the finite future, there will be no longer any energy transformations that can do work in the entire universe. And that's at an astronomical scale. Now, we don't really care about the astronomical scale in this class because we're thinking here in terms of things within the cell. We're taking about the other end of the spectrum, very small. So what about biologically? What does this mean? Well, again, biological processes are reaching equilibrium. I won't necessarily talk about the beginning, but we can talk certainly about the end. All biological processes are dying. They're in the process of reaching equilibrium. Whether that be a chemical reaction, whether that be an entire metabolic system within a cell, whether that be an entire cell, whether that be an entire organism. Those biological processes are reaching equilibrium. Now, as long as we provide energy from the surrounding and we keep pumping energy in from the surroundings, that equilibrium state can be avoided. Well, that's metabolism. You eat to avoid a state of equilibrium. If you stop eating and drinking water, you will reach equilibrium. You will die. Okay, and you know that. So we keep doing this, keep eating to avoid that state of maximal entropy so that there can be this constant flow of energy, constant work. Okay. Now, understand something, that then this driving force to reach equilibrium, we can quantify that, and that quantification can come as changes in free energy. Okay? A change in free energy is essentially a measure of the driving force for a particular something to reach equilibrium. Okay? And so we're going to look at this here in a little bit. Right now, let's take this one step further, and we'll think about this one final implication of this. Systems that are not at equilibrium can transfer energy in an orderly way. Right? That, I think, follows from what we've talked about with 2, that they're dying, but if they're not, if they're in the process of dying, they're still working. Right? And we have then 2 different types of systems that you would encounter, a reversible system or an irreversible system, and they're depicted here by these tanks, or these tanks of water that are separated by some dam. On the left here, we have an equal level of water. We'd say that this is reversible. Water can be exchanged through this dam, certainly, but it's not going to accumulate on one side or the other. It's at equilibrium. It's going from right to left as quickly as it's going from left to right. It's at equilibrium. And this cannot do work. There's not an orderly transfer of energy. Irreversible systems, these are the ones that are more interesting to us because our tanks of water are at 2 different levels. There's only one direction for the water to move, and that's from left to right, and it's going to move at a fast rate to do that. And this can then do work. Incidentally, it can also be regulated. We can close that dam, and we can decrease the amount of water moving from left to right, or we can increase it by opening it up further. So lots of different ways to do this. And this right here, those systems, irreversible systems, can do work. And not only that, but that is a biological system. All biological systems that are what we call living, they're not dead, right, are irreversible. That can be whether that's at a this enormous scale, okay, meaning your entire body or an ecosystem, or all the way down to individual reactions. For instance, okay, let's give a biological example. Let's think about an individual reaction, okay? And the individual reaction I want to think about is the hydrolysis of ATP. Equilibrium constant here, again, I don't need to review really what an equilibrium constant is, but products over reactants. Okay, that's our equilibrium constant, ADP, inorganic phosphate, and ATP, the concentration of those. Very important biological reaction. Now, when this reaction reaches equilibrium, this KEQ is going to be 200,000 to 1. It's going to be about 2 times 10 to the 5th. That's our value of the KEQ, meaning this, that whatever ATP was in the system is gone. It's all ADP and it's all inorganic phosphate. This reaction goes to almost a quantitative transfer of ATP to its breakdown products ADP and inorganic phosphate. When we find then a system with no ATP in it, or very, very little ATP and a very high concentration of ADP and inorganic phosphate, we say that that's a reversible system. That reaction is reversible. It's at equilibrium. Okay? Now, consider this. Okay? Irreversible. It turns out that in a cellular environment, the concentration of ATP relative to ADP and inorganic phosphate is about 18,000 times higher. ATP concentration is about 18,000 times higher than these, ADP and inorganic phosphate. That's a long ways away from this, its equilibrium point, which means that this is irreversible. It's like this system here. There's a chemical potential. And we can measure then that chemical potential by delta G, and we say that the delta G for this is negative 55 kilojoules per mole. It has this high driving force to reach equilibrium. It's not at equilibrium. It has a high driving force to get to it. Come back here, where we're at equilibrium, delta G is 0. There's no free energy there. It can't do work. Free energy, remember, is the portion of the system that can do work. And when it's at equilibrium, that's been minimized. And if it's been minimized, then we say 0. There's no potential to reach equilibrium. It's already at equilibrium. Okay, so that's how we think then about delta G and these things. So, just in summation then, we start here at the first and second law of thermodynamics to think about energy moving, in which direction they're going to move, and we boil that down from essentially astronomical scales all the way down to a single reaction in a cell. And every time we think about cells and we think about reactions in cells and we think about, in particular, metabolic systems and metabolic pathways, all those are irreversible. Metabolic pathways are. Not every reaction, though, in a metabolic pathway is irreversible. There are some that are reversible, but the metabolic pathway as a whole will be irreversible. And we'll talk about that as we move forward into the class. Now, I want to spend some more time on this, delta G. And I want to go through what exactly is the difference between standard free energy change and what we call actual free energy change. And we'll use these two different delta G values, so it's important to understand what is the difference really of these. Again, this is review. So standard free energy, let's look at this. The free energy change for a reaction occurring under a set of standard conditions. That's what delta G prime naught is. Okay, so we have this, delta G prime naught. The prime and the naught represent that we are talking about a free energy change under standard conditions. And the prime and the naught actually mean biochemical standard conditions, right? So a set of standard conditions. Now, what exactly is the purpose of this? Well, let's think about this. This is a reference, and I like to use another illustration. Denver, the Mile High City. Why do we call it the Mile High City? Because it is 5,280 feet above what? Above sea level. 5,280 feet above sea level, and sea level is then our reference point. We, as a international group of people, have agreed that we're going to measure elevation off of a certain reference, and that reference is always going to be sea level. So you have Death Valley in Nevada that's below sea level, whereas you have Long's Peak that's about 14,000 feet above sea level. But it's all relative to that reference point. And that reference point is somewhat arbitrary. Why didn't we pick the top of Mount Everest as our reference? Well, we didn't. We'd have all negative, of course, elevations if we did. And we could have done that, but we didn't. We picked sea level. Okay, so that's a reference. The standard free energy and the changes in standard free energy are a reference. And essentially what we're saying is that under these conditions, our delta G is such and such, and that then tells us how far that delta G, or how far that reaction is from equilibrium starting under our reference point, our standard free energy. Now, what are standard conditions? Let's go ahead and look at this. We are going to, because we're biochemists, we're going to be looking at, of course, biochemistry standard conditions, which always gives us delta G prime naught. Now, some books will go delta G naught prime. Your book goes prime naught. I don't really care. We're going to use this because the book that we're using uses this, but either one is fine. If you're taking a chemistry class, you'll talk about delta G naught without the prime. And essentially, the difference between these two is going to be found in these. It's going to be found in these, okay? These, 1, 2, 3, these conditions are the same in chemical and biochemical standard conditions. You're going to set the temperature at 298 K, which is essentially 25 degrees Celsius, room temperature. Pressure is at 1 atmosphere is what you find at sea level. And then this is the really important point for our discussion. The reactant and product concentrations are going to be equal, 1 to 1. There's a 1-to-1 molar ratio of product reactants under standard conditions, okay? Now, the biochemist goes on and says, okay, well, we're going to set pH at 7. We're going to set water to 55.5 molar. We're going to set magnesium to 1 millimolar. The reason being that you very rarely will see changes in these three. So we like to keep them the same, and we just say, well, they're constant on both sides of the equation, and because of that, they cancel each other out. So if you have this reaction, this is ATP hydrolysis. ATP, we didn't say this the first time we saw this, but ATP, generally speaking, is in complex with magnesium. Okay, well, we can ignore, when we start to report an equilibrium constant for the ATP hydrolysis, we can ignore the effects of magnesium. It's equal on both sides. Now, while water doesn't appear on both sides, it's going to be constant. You're not going to change the concentration of water. So we just, right, it's constant on both sides of the equation. Same with the pH. It's going to be constant. Right, so we ignore even this, right, the concentration of protons in our equilibrium expression. Right, so that would be the main difference. Now, again, this is going to be an important point here. Let me highlight this. Under standard conditions, we're going to start with this at 1 molar. We're going to start with this at 1 molar. We're going to start with this at 1 molar. And then we're going to measure our free energy change. That's our starting point. Just like sea level is our starting point for measuring elevation. Now, that brings us to this. One of the most fundamental thermodynamic equations found. And what we're saying here is this: changes in free energy under standard conditions are dependent upon essentially the equilibrium constant. This is a measure of the equilibrium constant, or how far a particular reaction is from equilibrium under standard conditions. Now, R, universal gas constant, that can be found in your book, right? The value for that, chapter 13. But let's think about this idea that this is a measure of how far a particular reaction is from equilibrium under standard conditions. And let's go to this table. This is a table very similar to what you find in your book. And what I want to do is take a reaction that has, this equilibrium constant, 1 times 10 to the negative 6, and another reaction that has this equilibrium constant, 1 times 10 to the 6. Two ends of the spectrum. There are 12 orders of magnitude apart from each other. The reaction in green represents a reaction that is very endergonic. It has a driving force to make reactants to reach equilibrium. It heavily favors reactants. The opposite would be true of the one in blue. It has a driving force to reach products, or to make products reach equilibrium. It heavily favors products at equilibrium. So those are our two ends of the spectrum. Now, when you look at then the delta G values for this, here and here, down here, the only difference between these two is not the magnitude, but the sign. Now, the magnitude is the same, 34.2. That magnitude tells us that both of these reactions are the same distance, if you will, or they have the same driving force. That would be a better way to think about it, from equilibrium under standard conditions. But those driving forces are in opposite directions. The one on top has a positive sign, which means that it will go towards reactants to reach equilibrium. It's endergonic. The one on bottom has a negative sign, meaning that it will go towards products to reach equilibrium. It's exergonic. And that's the major difference. We'd say that this can do work as it goes towards equilibrium. We'd say that this one has to have work done on it, okay, to keep it from equilibrium. So that's how we think about standard free energy changes. Essentially the distance and the direction that equilibrium is under those set of initial conditions. Just like we think about elevation gain or loss. Starting at sea level, how much am I going to gain or lose as I go to Death Valley or to the top of Long's Peak? Now let me say this, okay? Let's go one step further. What about this one? Equilibrium constant is 1. Well, at 1, you're already, and under standard conditions, you're already at equilibrium. Because remember, our product to reactant ratio, product to reactant concentration ratio, or molar ratio, at standard conditions is 1 to 1. Well, equilibrium for that particular reaction is 1 to 1 as well, so you're already at equilibrium. This would be like going from San Diego to San Francisco in terms of elevation, gain or loss. They're both at sea level. You're not going to gain or lose anything. Right? That's the same idea here, and we say that delta G is 0. Anytime you see delta G 0, then this system's at equilibrium and can't do work. Okay. Right. Now that's it for standard free energy. But what about actual free energy? Meaning this: what if conditions aren't standard? And they rarely are. I mean, the cell is not under these arbitrary set of standard conditions. So what if that's the case? How do we then deal with that? We'll have to have a different than delta G value. And we call this actual free energy. It's delta G, not delta G prime, not just delta G. And this is the change in free energy of reaction is determined by a set of initial conditions that are not, and that's the key thing, not standard. So they're a different set of initial conditions. That's all we're saying. Now, let's do this. We'll use my analogy and my illustration here in a little bit. Well, let's use the illustration first, and then we'll get to this. Right? Let's say that I wanted to measure my elevation gain as I went from not sea level, but Fort Collins to the top of Long's Peak. If I went from sea level, then it's going to be 14,000 feet, somewhere around 14,000 feet. But if I go from Fort Collins to the top of Long's Peak, my elevation gain is going to be somewhere around 9,000 feet, not 14,000 feet. Okay, so that's the difference. And so we have an actual elevation gain. Well, that's the same idea here. We're starting at a different point. Right? So, for instance, go back to this reaction here, ATP hydrolysis. Under standard conditions, we say that this is 1 molar. We say that this is 1 molar. and we say that this is 1 molar. But what if we were to say, look at the human erythrocyte? Okay? Meaning the red blood cell. Well, ATP concentration is not 1 molar, it's 2.25 molar. And ADP concentration is not 1 molar, it's 0.25 molar. And inorganic phosphate is not 1 molar, it's 1.65 molar. We're starting at a different point. We're not starting at the same point. We're not under standard conditions. We're starting at Fort Collins to get to Long's Peak, not sea level. And so what do we do here with this? Well, we can get this Q value for this. What is Q? Q is just essentially the concentration of products of reactants. So in this case, we'd have 0.25 being the concentration of ADP times 1.65 being the concentration of inorganic phosphate divided by 2.25. Okay, and that's our Q value. Q is equal to that. Okay, and this should be 0. You could convert these numbers to molar. I mean, these are millimolar, but either way, it'd be the same thing. Okay, but you could do that, and it depends on what you decide your units are for R, your gas constant. But this is Q. That's your starting point. Now, we then calculate actual free energy changes by saying, well, that's equal to the reference, our equilibrium constant, essentially, or the way we're depicting it, standard free energy change, plus RT natural log Q, our new starting point. Okay. Now, understand this. Okay, for this ATP reaction, delta G prime naught is equal to negative 30.5 kilojoules per mole. However, if we were to take this in the erythrocyte, Q, given that Q, delta G would be somewhere around negative 52 kilojoules per mole, somewhere around there. And I'd have to go back and do the calculation again, but that'd be about that. So, in the human erythrocyte, because ATP concentrations are so much higher than the product, then there's a much greater driving force to reach equilibrium than there would be under standard conditions. Because under standard conditions, ATP is in equal concentration to the products. Right? So that's the difference between these two. And that's really our take-home message. That the starting point, or your Q value, is going to determine your actual free energy change. Okay? Now, you can go on and do this mathematically, but the take-home for this is that if Q is greater than the KEQ, delta G is positive. If Q is less than the KEQ, then delta G is negative. And if Q is equal to KEQ, delta G is 0. Is equal to 0. Okay? Now, just to give you an illustration why this last one's the case, and you can do the math from there on, but if you think about this, this is negative RT natural log KEQ. Well, if KEQ is equal to Q, then you have a negative number plus the same positive number, and delta G has to be 0. Okay, and you can do the rest of the mathematics from there. Okay. Now, last thing to say here with free energies, they're additive. A very important concept. You already probably know this. All right, but we are going to take, for instance, a reaction where we make glucose 6-phosphate, right? Phosphorylate glucose, making glucose 6-phosphate. If we were to take that without ATP, delta G is positive 13.8. ATP hydrolysis, right, at standard conditions, negative 30.5. If we couple these two reactions, then the total delta G is negative 16.7 kilojoules per mole. Here's another example of making glutamine from glutamate, which we'll talk about later on in this class when we look at amino acid metabolism. However, when you look at this, they're just additive. Now, how is that the case? Well, enzymes. Enzymes have the capacity to couple these two reactions. For instance, in this case, what's going to happen is that there's a hydroxyl on the 6th carbon of glucose that's going to act as the nucleophile to attack the final phosphate, the gamma phosphate on ATP, and that will then couple the hydrolysis of ATP with the phosphorylation of glucose, making glucose 6-phosphate in what's called the nucleophilic substitution reaction, right? So, or group transfer reaction. So, and then we just add these delta G's up and we get a new delta G. This is a reaction that favors the production of glucose 6-phosphate and is driven in that direction by ATP hydrolysis. ATP is providing the work or the energy necessary to make glucose 6-phosphate. Okay? Right. Hopefully you understand these things. If you don't, by all means come and talk to me. certainly read, what is it? I think pages 506 to 511. It talks a little bit more about these things. And that's it.